Welcome to AI Paper Slop, where we summarize the latest AI and tech papers directly from the King. Today we are looking at A Bitter Lesson for Data Filtering by Christopher Mori, John Ducci, and Tatsunori Hashimoto out of Stanford.
Yeah, it's a fantastic paper.
It really is. And we're jumping right into the core insight here. This paper mathematically and empirically proves that if you have enough compute, filtering your pre-training data it's actually detrimental.
Right, which is wild. The researchers basically show that in a high compute regime, so using large models above like 330 million parameters, they don't just tolerate raw, unfiltered junk data from Common Crawl. They actively learn better representations from it compared to heavily curated datasets.
Exactly. And by extrapolating their scaling laws, they project that training directly on the raw, completely unfiltered 240 trillion token Common Crawl pool is going to become the optimal pre-training strategy at around 1M plus 30 FLOPs.
Yeah, and I mean, the magnitude of that finding really cannot be overstated for you guys out there managing data pipelines right now. Because the prevailing wisdom in modern pre-training is that you absolutely must aggressively filter data sets to maintain quality.
Oh, yeah. Garbage in, garbage out, right?
Exactly. That's the heuristic. But what Stanford is presenting here is a direct challenge to that. If you give a sufficiently large model enough training steps, meaning you epoch over your data, the model essentially learns to isolate and ignore the noise internally.
Which is just crazy to think about.
It is. We are looking at a future where throwing raw compute at unfiltered internet slop actually yields a mathematically superior model than, spending months handcrafting complex heuristic filters.
Right. So if you are currently burning massive compute cycles running filters like DCLM baseline or refined web, this paper suggests you're fighting a losing battle against the bitter lesson of compute scaling. But to understand the mechanics of this, we need to look at how the Stanford team proved a theory about 240 trillion tokens without actually having the infinite compute required to train on that massive pool.
Right, they had to simulate it.
Exactly. My reading of the methodology is that they essentially created a microcosm of the scaling laws. They scaled down the data pools, but they kept the relative proportions of clean to junk intact. So they were looking at pools ranging from 670 million to 10 billion tokens.
Yeah, they engineered this highly controlled fractional environment. Since they couldn't run the full data set, they used the metalingual library to train a series of llama-style dense transformers. And they started with tiny models, like around 15 million parameters, and scaled all the way up to 7 billion parameters.
Wow, so a pretty huge range.
Right, and this dual-axis scaling, adjusting both the model capacity and the number of training steps that gave them the empirical data they needed to map the exact crossing points where raw data begins to outperform filtered data.
And they tested this against the industry standard filters, right? They ablated an English language filter using a fast text classifier, a repetition filter, and a stop word filter.
Yeah, all the usual suspects.
And then they tested against the real heavyweights, refined web, which retains about 13% of the raw data, and DCLM baseline, which is just incredibly aggressive. I mean, it leaves just 2.1% of the original text.
It's basically throwing everything away.
Right. And this is where the paper's argument about data scarcity really hits home. We operate in a reality where we are absolutely starved for high-quality tokens.
Yeah. Token starvation is the bottleneck right now.
Exactly. The industry trend isn't just hitting chinchilla optimality anymore. It's overtraining smaller models relative to chinchilla just to make inference financially viable.
Yeah.
So wait, by using a filter like DCLM baseline that throws away nearly 98% of your data, aren't we actively accelerating token starvation? Like, we're forcing our pipeline into earlier and more frequent epoching.
You absolutely are. And the heuristic trap of filtering becomes really obvious when you look at those overtraining trends. Like, filtering absolutely works in a compute-constrained environment, which is why it became the default practice in the first place.
Because you can only afford to look at the good stuff.
Exactly. If your FLOP budget only allows for a single epoch over a small data set, every single step must be on high-signal text. But by removing 98% of the data, you artificially compress the diversity of your pre-training distribution.
Okay, I see.
And the Stanford researchers identified that this aggressive curation fundamentally caps the model's asymptotic performance. When you're willing to spend the compute to train longer, the raw, uncompressed distribution of Common Crawl, even with all its noise, it just contains a broader spectrum of latent information.
Let's trace how that actually plays out empirically in their 670 million token pool experiment. Because this is where the anomaly of scale really becomes visible.
Yeah, the crossing point.
Right. So when they trained the 15 million parameter model, the conventional wisdom held up perfectly. The filtered datasets, specifically refined web, easily outperformed the unfiltered pool.
Makes sense.
But as they scaled the model size up to 330 million and then to 1 billion parameters, the loss curves totally inverted.
Which is the crazy part.
It really is. The raw common crawl pool eventually beat every single filtered variant. I think it hit a negative log likelihood loss of 3.37 on the 1B model.
Yep, that's right.
The hardware analogy I keep coming back to is processing a massive, messy data stream. A 15 million parameter model acts like a simple microcontroller, right?
Right.
It simply doesn't have the internal memory or processing overhead to handle noisy input, so you have to clean the signal before it reaches the chip.
Exactly.
Yeah.
But a 1 billion parameter model.
Yeah, it's like a massive multi-core processor. It has enough parameter overhead to just dedicate a subset of its weights purely to modeling the noise distribution.
Yeah.
And that cleanly separates it from the high-quality signal.
Yeah, the internal allocation of parameters is precisely the mechanism driving this. And we see the visualization of this in Figure 2 of the paper, plotting the Pareto frontier of compute against performance.
Right, the Pareto frontier.
So at the low compute end, the unfiltered pool is obviously the worst performer. But at the high compute end, it transitions to being the absolute optimal choice.
Wow.
And what's particularly revealing about that Pareto frontier is the performance of the repetition filter. It never even touches the optimal curve. At every compute budget they tested, there were always at least 2 other data sets performing better.
Wait, really? Because our assumption has always been that repeated text is just uninformative, you know? That it just causes the model to memorize boilerplate code or like SEO spam.
Right, that's the standard thinking.
But if the repetition filter is mathematically suboptimal, the gradient descent process must actually be utilizing those repetitions in a productive way somehow.
Yeah, exactly.
My guess is that the repetitions are acting as a natural weighting mechanism, like reinforcing certain latent pathways without fundamentally altering the target distribution.
That's a great way to put it. The gradient is highly efficient at extracting signal. And repeated text, rather than just being a waste of compute, acts as a structural anchor.
A structural anchor. I like that.
Yeah, so when a model encounters repeated boilerplate, a sufficiently large architecture doesn't just blindly memorize it at the expense of other knowledge. It maps that highly predictable sequence to a very narrow, log-dimensional subspace.
Okay, so it tucks it away.
Exactly. And once that subspace is formed, the model expends almost zero energetic cost in terms of loss gradients when it sees that repetition again.
Ah.
The filter, on the other hand, requires a human to guess what frequency of repetition is bad. And that is an arbitrary heuristic that ultimately degrades the overall density of the dataset.
That makes total sense. And that brings us to what I consider, honestly, the most counterintuitive part of the whole paper.
The junk injection.
Yes. Ignoring passive noise is one thing, but the Stanford team didn't stop there. They actively tried to break the model by force-feeding it concentrated garbage just to test its robustness.
It's a phenomenal stress test.
It really is. So they injected 2 types of active corruption into the common crawl pool. First, randomly generated strings of 3 to 8 characters, forming fake words. And second, actual common crawl documents where the word order was entirely shuffled into nonsense.
Complete word salad.
Exactly. And they scaled this junk up to plus 800%. So the untouched natural documents only made up 10% of the entire training pool.
Which is just an insane ratio. I mean, the expectation when 90% of your data is literal garbage is catastrophic forgetting.
Right.
You would fully expect the model's ability to generate coherent English to completely collapse. But instead, not only did the 330 million and 1 billion parameter models maintain their capabilities, but after about 11 billion training tokens, something incredible happened.
The models trained on the shuffled Word documents actually surpassed the performance of models trained on the clean, untouched common crawl pool.
Yes, which is mind-blowing.
I really want to isolate the mechanics of this. Because how does a model improve its natural language prediction when 80 to 90% of its diet is a shuffled word salad?
It feels completely paradoxical.
It totally does, until you look closely at how transformers actually build attention maps.
Right, so the underlying mechanism here relies entirely on the unigram distribution. When you take a coherent sentence and shuffle the words, you destroy the local syntax. The grammar is just gone.
Okay, sure.
But the document-level co-occurrence remains perfectly intact. So the words France and Paris or, Python and def still appear in the exact same context window.
Interesting.
For a small model, this is devastating because it relies heavily on local syntactic crutches, like positional proximity, to predict the next token. It lacks the dimensional capacity to look deeper. But a large model operates differently. Because the syntax is randomized, the attention heads cannot rely on simple proximity anymore. They're forced to work much harder to minimize the loss, which forces the model to construct far more robust, deeper semantic clusters.
Wow. So the shuffle data is basically acting as an extreme data level form of dropout.
That's exactly what it is.
By removing the easy syntactic clues, you force the transformer to learn the fundamental underlying relationships between the concepts themselves.
Yep, it has to learn the actual semantics.
That perfectly explains why the shuffled text improved performance, while the random character strings just acted as neutral noise that the model eventually ignored.
Precisely.
But mapping this 670 million token experiment to reality requires scaling laws. If you are building frontier models today, you need to know how this applies to the 240 trillion tokens in DCLM pool.
Right, the actual internet.
Exactly. So the authors derived a step count function, they called it n star of m, m, to calculate the exact crossing point where raw data beats filtered data based on model size m and pool size m.
And the critical detail in that function is that the crossing point scales superlinearly with the pool size.
Okay, unpack that for me.
So they observed that for a 2 billion token pool, the unfiltered data overtakes the filtered data after about 3 epochs. But when they expanded the pool to 10 billion tokens, it required 10 epochs to cross over.
Ah, I see.
The reason for this superlinear scaling is the sheer diversity of the noise. As you increase the volume of raw common crawl, the number of unique noise patterns and structural anomalies just grows exponentially.
Because the internet is weird and varied.
Extremely varied. So the model requires significantly more forward and backward, passes more training steps to encounter all those variations, identify them as noise, and cleanly isolate them into separate representational spaces.
Which means the compute required to overcome the noise grows aggressively as the dataset grows.
Exactly.
So to project out to the full 240 trillion tokens, they used 2 scaling fits. One was based on the DeepSeek v4 token per parameter ratio, and another based on a strict 4 epoch constraint.
Yep.
And both fits were highly linear on a log-log scale with an R-squared above 0.99. And both pointed to a staggering compute target, 1E plus 30 FLOPs.
Which is just a massive, massive number.
Grounding that in today's hardware reality, current estimates for cutting-edge frontier models like Grok 4, they hover around 5E plus 26 FLOPs.
Right.
So 1 plus 30 is about 10,000 times more compute than the largest training runs happening right now.
Yeah, we aren't quite there yet.
The death warrant for data filtering definitely has a date on it, but we are still waiting for the hardware clusters to scale by 4 orders of magnitude.
Yeah, the timeline is entirely hardware dependent, but the mathematical certainty of that destination is really what matters here. The authors didn't just provide empirical graphs, they grounded this in theoretical guarantees.
Right, Section 7.
Exactly, Section 7. They introduced Proposition 7.1, analyzing rank necessity under orthogonal inputs.
Okay, let's get into the math a bit.
So if we model the neural network as a linear transformation of rank R, and the training data consists of multiple distinct distributions or tasks, so some high signal text, some random noise, the proof demonstrates how gradient descent handles that mixture.
Right. When I read that section, my understanding was that as long as the model's capacity, its rank R, is strictly greater than the number of distinct tasks in the data, the gradient descent naturally isolates the noise.
That's spot on.
Because the model has excess dimensions, it maps the noisy data to a subspace that is mathematically orthogonal to the subspace used for the high-quality text.
Precisely.
So the noise literally cannot interfere with the language generation capabilities because they exist in parallel, non-intersecting planes within the latent space.
Yeah, it aligns perfectly with the geometry of high-dimensional spaces. The noise doesn't overwrite the signal. It just occupies a previously unused corner of the parameter space.
That's what?
Because the capacity is so massive, the optimal fit for the good data remains entirely unperturbed by the presence of the bad data. The gradient descent process basically acts as a flawless automated sorting algorithm, pushing unrelated distributions into their own isolated dimensional pockets.
It is incredibly elegant from an architectural standpoint. But I do want to push back on one critical edge case here, which is covariate shift.
Ah, right. Factuality.
Exactly. It's one thing to map random characters or shuffled word salads to an orthogonal subspace, but what happens when the bad data is structurally identical to the good data, but it's just factually incorrect?
Yeah, that's the danger zone.
If the raw common crawl contains 10,000 instances of a misconception, for example, confidently stating the capital of Australia is Sydney, the model isn't going to recognize that as noise. The syntax is perfect. The formatting is identical to a factual encyclopedia entry.
Right.
It's going to learn the misconception.
And that shift in the conditional distribution is the primary theoretical vulnerability of training on unfiltered internet data. The model cannot distinguish between a factual truth and a widespread misconception based purely on syntax. It relies entirely on frequency.
Right.
So to quantify this risk, the researchers ran a massive GPT-5 mini analysis focusing on MMLU benchmarks.
Okay, how did they test that?
They wanted to see if the raw common crawl actually contained enough unified, identically formatted misconceptions to override factual truths. So they looked at fields with rare keywords, such as world religions, astronomy, and medical genetics.
Nice.
And they measured the ratio of documents supporting the factual truth versus documents actively refuting it.
My assumption would be that for highly specialized or technical fields, a single pervasive piece of misinformation could easily dominate the relatively small number of mathematically accurate documents.
It is a totally valid concern, particularly for niche domain knowledge, but the scale of the internet actually provides a surprising buffer here.
Oh, really?
Yeah. Their analysis showed that for world religions, documents supporting the MMLU factual answers outweighed refuting documents by a ratio of 5.89 to 0.00.
Wow, that's decisive.
Even in astronomy, the ratio was 2.03 to 0.14.
Okay.
The finding here is that while the internet contains a massive volume of incorrect information, that incorrect information is highly fragmented. Misconceptions do not share the same uniform, repetitive structure that factual truths do.
Ah, I see.
Factual data, like the actual capital of Australia, is repeated uniformly across millions of distinct domains, educational sites, and databases. The truth, purely by structural redundancy and volume, dominates the highly scattered covariate shifts.
That makes a lot of sense. So even when the model encounters confident inaccuracies, the gradient ultimately follows the heaviest, most consistent distribution, which overwhelmingly tends to be factual consensus.
Exactly.
Stepping back and looking at the entire paper, this research serves as a profound vindication of Richard Sutton's famous 2019 essay, The Bitter Lesson.
Oh, absolutely.
Sutton pointed out that throughout the history of AI, researchers have continually tried to inject human knowledge and human-designed heuristics into their systems.
Right. We can't help ourselves.
We spent decades handcrafting feature extractors in computer vision, trying to explicitly teach models how to see edges and shapes, and eventually massive compute and raw pixels completely swept all those human heuristics away.
The parallels are exact. We are currently in the handcrafted feature era of data curation. We employ massive teams of engineers to build fast text classifiers, tweak repetition thresholds, and, argue over the exact optimal retention rate of refined web.
Yeah, guilty as charged.
We are trying to explicitly teach the model what good data looks like. But Mori, Ducci, and Hashimoto are mathematically proving that our human intuition about dataset purity is actually a bottleneck.
Wow.
Compute scaling and the gradient descent algorithm will eventually sweep our data filters away, just as they swept away feature engineering.
And that reality is something you need to deeply consider if you are architecting systems today. We are looking down the barrel of a 1E plus 30 FLOP future.
It's coming.
It is. If optimal pre-training eventually requires nothing more than dumping the entire unfiltered contents of the internet into a cluster and letting the gradient sort it out into orthogonal subspaces, how does that change your focus as an ML engineer?
That's the million-dollar question.
In an era where you have virtually unlimited compute, the art of data curation evaporates. It ceases to be a nuanced heuristic challenge and simply becomes a problem of industrial plumbing.
Yep. Just moving bits.
Exactly. How fast can you move 240 trillion uncompressed tokens from storage to the GPUs? The future of machine learning might be entirely about designing architectures capable of scaling to accommodate that noise, rather than trying to clean the noise before it hits the model.
A bitter lesson for sure.
A bitter lesson for our data pipelines, indeed. Something to mull over until our next paper dive.